Okay, in this presentation we are going to look at hypothesis testing for population variance. Okay, so we have an example here where we have components for washing machines. So suppose a machine produces circular parts for washing machines. Okay, a random sample of 10 circular parts is selected and the variance is found to be 0.7 centimetres. The machine is producing the correct standard of circular parts if the variance of the diameter is no greater than 0.4 centimeters. Suppose that the sampled measurements are normally distributed. Okay. Hypothesis test may be carried out to determine whether or not the machine is producing the correct standard of parts. Okay, so let's do that test. So, to determine whether the machine is producing parts with the correct standard of variance, we will perform a hypothesis test for the population variance. Okay. Specifically, we will use a chi-square test for variance. And here is a step-by-step solution. So this is what we're going to be doing here. Okay. So the first step is to find the null and alternative hypotheses. So the null hypothesis H0. The machine is producing parts with the correct variance of sigma squared equals 0.4 centimeters squared. Okay, so H0 sigma squared equals 0.4. Okay, the alternative hypothesis is that H1, the machine is not producing parts with a variance of sigma squared equals 0.4 centimeters squared. Okay, so H1 sigma squared not equal to 0.4. Okay, so this is a two-tailed test, just as a remark. Okay, it doesn't really tell us the significance level, but we'll just use the significance level of 0.05 as it's sort of standard in many undergraduate courses and master's courses. So not that that's, anything that's a law or anything. It's just a sort of, unless you're told in the exam, just go with 0.05. Okay. Now this is the key part here, the test statistic. The test statistic for variance using a chi-squared distribution is as follows. Chi-squared equals n minus 1 times s squared, where that's the sample variance, divided by sigma squared. Okay, so here n is the sample size, which is 10 in this case. S squared is the sample variance, which is 0.7 cm squared. Okay, and sigma squared is the population variance under the null hypothesis. Okay, that's 0.4 centimeters squared. Okay, so our test statistic is as follows. Chi-squared equals 10 minus 1 times 0.7 divided by 0.4. So 9 times 0.7 divided by 0.4, that gives us 6.3 divided by 0.4, which is 15.75. So for a two-tailed test with alpha equals 0.5 and degrees of freedom n minus 1, which is 9, 10 minus 1, the critical chi-squared values can be found using a chi-squared distribution or a calculator. Okay. Now, I will not get into how to calculate the chi-squared critical values here. Probably you've seen this stuff before. You might have seen chi-square goodness of fit test. So that's actually how we would sort of calculate this as well. So I won't get into how to calculate the critical values in this case. Using chi-square tables or calculator, we find the following. So we're going to look for the upper and lower bound of chi-squared interval. So the critical value for the lower tail is chi-squared 0.025 and 9. Okay, recalling that it's a two-tailed test and a significance level of 5%, 0.05, which is, that means we have an interval from the 2.5% quartile to the 97.5% quartile with 9 degrees of freedom. That is an interval from 2.70 to 19.05. Okay, that's the upper and lower bound essentially of the upper and lower critical value. Okay, so essentially the question is our test statistic in that interval between 2.7 and 19.02? Yes, it is, because it is 15.75. Is it 15.75? I just backtrack a bit. Yes, it is 15.75. So we reject the null hypothesis if the test statistic falls outside the range defined by the critical value. So this is what we have to ask ourselves here. Is our chi-square test statistic between 2.70 and 19.02? And yes, it is. It is 15.75. So it is within our range. So we failed to reject the null hypothesis at a 5% significance level. Okay. So what does that mean? There's not enough evidence to reject the null hypothesis. Therefore, we can conclude that the machine is producing circular parts with a variance that is not significantly different from 0.4 centimetres squared, and this suggests that the machine is producing parts that meet the desired variance standard. Okay, or well, it doesn't suggest it really. That's a bit of a, but it just we've no evidence to say anything contrary to that. What I really should say there. Anyway, I'll stick with what I have there because I think you get the idea. The first bullet point is the key one there. There's not enough evidence to reject the null hypothesis, which is the headline essentially for this part. Okay, we'll leave it there.